Good afternoon, students. Today we begin with polarization of light. Very important chapter and an interesting one in optics. So, what is polarization about? So far, what you have learned about interference and diffraction, right? And this interference and diffraction confirms the wave nature of light. The wave nature of light is depicted by the processes, and what it doesn't predict is what kind of nature does light wave have, whether it is transverse or whether it is longitudinal. Now, can you tell me what is the difference between a transverse wave and a longitudinal wave? Okay, that is my first task to you. Please write down the difference between a transverse wave and a longitudinal wave. And we are going to see that this phenomena of polarization establishes the fact that light waves are transverse in nature. And let us see how. So light waves are nothing but electromagnetic waves. We have already learned about it in our junior classes. Now it is made up of what? It is made up of electric field and magnetic field, right? And electric field is represented by vector E and magnetic field is represented by vector B, and these two are perpendicular to each other, isn't it? And they are also in phase with each other. And along with this, both of them are perpendicular to the direction of propagation. So all these things we have already learned in our chapter called Maxwell's equation. Well, in more details actually, with much more mathematical expressions and all, if you remember, right? So this is what light waves are about. So this can be more clear if I show you some diagrams. Okay, here is one. You see, here we have the electric field and magnetic field vectors, and they are represented by these red arrows and the blue arrows respectively. So this is my electric field and this one is my magnetic field. Magnetic field variation is perpendicular to the electric field, right? And electromagnetic waves transport energy through empty space stored in the propagating electric and magnetic fields. We all know that electromagnetic waves can flow through vacuum, isn't it? So, how do they transport the energy? Through the storage through these two fields. And a single frequency electromagnetic waves, what does it do? It exhibits a sinusoidal variation of electric and magnetic fields in space. That you can see, this is a single electric field moving sinusoidally, and this is the magnetic field perpendicular to the electric field. It's also sinusoidal. So as you can see, as the second point tells us that the electric field and the magnetic field are in phase, that you can easily see that they are in phase with each other. Okay, here is one more diagram over here. So what is that diagram? Let us see. Yes, this one. So you can see here the red one and the blue one represent electric field and magnetic field respectively, and both of them are again perpendicular to the direction of propagation. So this is a fact which we have already learned. We have proved it rather mathematically that the direction of both electric field and magnetic field are perpendicular to the direction of propagation of electromagnetic waves, isn't it? Now, what is unpolarized light? Well, unpolarized light contains number of atoms producing electric field in a particular orientation. What does it mean? How are electric field produced? You all know that. Okay, electric field is produced due to charges, and those charges are contained in atoms, we can say. So these charges producing electric field can have their orientation in all possible directions and not particularly in a particular direction, right? So you have seen the vectors in the previous diagram, that the vectors are just in a particular direction and that can have different angles, right? So what is the resultant electric field? It is the superposition of all these waves vibrating in a particular direction. That gives you the resultant wave of propagation. Now the question is that, have you noticed that when I am explaining to you unpolarized light, what I am telling you only about electric field. But if electromagnetic wave is made up of both electric as well as magnetic field. Then why are we only concerned with electric field and we are not talking about magnetic field? Well, I need to tell you the answer for that. Well, from Maxwell's equation, we can derive that electric field and magnetic field are related through this relation. E is equal to B into C. So what is my B? It is E by C. And what is C? C is the velocity of light, which is very, very high, we know, which is having a value of 3 into 10 to the power 8 meter per second, isn't it? So what do we find here? That B is actually 10 to the power minus 8 times of that of E, which is much, much small in magnitude, isn't it? So if we compare the magnitudes of E and B, then the magnitude of magnetic field is very low and hence it can be neglected. And that is why when we are talking of unpolarized light, we are talking only of electric field and not of magnetic field. Okay, so that you should keep in mind. Now we go to what is polarization. Well, polarization is nothing but restriction of electric field vector in a particular direction so that the vibrations are taking place in a single plane. Okay, so as I have told you just now that the electric field vectors can be vibrating in various orientations. In totally, if you consider the entire 3D space, they can be vibrating all over in a 360-degree plane. Can you understand that? Okay, something like, what can I say? If you put the arrow and if you just move it in a circle, okay? So what does it happen? That we can have the orientations of electric field in all possible directions. Okay, just if you spread your fingers and if your thumb represents a particular orientation, then your forefinger, middle finger and all these can be some other orientations of electric field. So what does polarization do? It restricts the electric field vector in a particular direction. Okay, and this is obviously the characteristic of transverse wave. Why? Because longitudinal waves can't be polarized. Why? Because their vibrations are always along the direction of propagation. So we cannot restrict the direction of propagation and hence we cannot restrict the vibrations of longitudinal wave because they are parallel to one another. So this is a characteristic of transverse wave only when we can restrict the vibrations in a particular direction. So that is an important characteristic which shows that polarization definitely proves that light is transverse in nature. Okay, now let me show you some figures and diagrams which makes the point clear. Well, here are two diagrams. As you can see, I've told you the orientations can be in all possible directions. So look here, these are my electric field vectors, the envelopes that I've already shown you earlier, and this can be in all possible directions. And here is my Polaroid, or which is my polarizer. Okay, and you can see it has been drawn in the form of a slit. Okay, and it is parallel. So what will happen? All the other orientations except the perpendicular one will be cut off. Do you understand? It is like chopping off the other parts except the one which can pass through the slits of the Polaroid. Well, mind it, there are no slits in a Polaroid. Okay, it's just for your understanding that as if there is some axis through which a particular orientation of vibration of electric field can pass. So you can see all the other wings have been chopped off and which we are left with only this particular orientation of electric field. That means we have restricted the vibration of electric field only along a certain plane, and that is my polarized wave. Now we take another Polaroid and we keep it over here. As you can see here, we have just rotated the axis by 90 degrees and it cannot pass through it. Okay, same thing is represented over here. So we have polarizer 1 and polarizer 2. Again here I have shown the orientations of electric field, which is the unpolarized beam of light, and all the other orientations, all the other electric field vectors are chopped off except the one which is parallel to these grooves. Okay, mind it, polarizer doesn't have grooves. This is only for understanding. I will explain to you what actually happens. Okay, so that will be explained to you, don't worry. And what happens is only this particular orientation passes through the polarizer 1, and if polarizer 2, which is not kept vertical like this one, and it is kept horizontal, then what happens? It bars the light from flowing further. So what can you see on the other side of this? Nothing. You cannot see any light. But what happens if you keep it vertical, I mean same as this one, then obviously you can see some light. But what will happen to the intensity? This was having a lot of intensity because lot of waves were together, but here only one certain orientation is passing, so naturally the intensity will be much smaller. Okay, so now let's see one more diagram. So here is my light source, and this is not the previous 3D diagram, but this is a 2D diagram which is representing the light waves vibrating in any direction. Okay, and here is my polarizing filter or whatever, and you can see as we have restricted the polarized light to vibrate in only one particular direction. Okay, so this is what is polarization. All right, now way of depicting polarized and unpolarized light waves. Now when we are trying to draw a polarized light and unpolarized light on a copy, then how do we do it? Okay, this is the symbol for ordinary light or unpolarized light. Okay, so we have an up and down arrow, and here is a big dot. Okay, this big dot actually represents the vibration perpendicular to this screen. Do you understand? If you just move this arrow and move it towards yourself, so that is the arrow which is perpendicular to the screen. All right. Now this is a plain polarized light having vibrations in the plane of the paper, or rather plane of the screen now I'm talking about. So the vibrations are restricted only on the plane of the paper or the screen. And if we can have a different polarization, plain polarized light, but having vibrations perpendicular to the plane of the paper. So as you can see, here the vibrations are taking place in and out of the screen. Okay, so these are two types of plain polarized light. One perpendicular to the plane of the screen, another on the plane of the screen. So this is the way of depicting the polarized and unpolarized light wave. Now we come to two important definitions. One is your plane of vibration and the other is plane of polarization. Well, we have got a figure over here. This is my unpolarized light, and as you can see, we have used the symbol over here. This is the vibration, okay, on the plane of the screen and perpendicular to the plane of the screen. So when they fall on this polarizer, and you can see this is the optic axis, so we can think of two imaginary planes, this yellow one and the purple one. Okay, so this yellow one is along this axis and this purple one is perpendicular to this axis. Okay, so what happens, as you all know, so which part will be cut off? Obviously the one which is perpendicular, and the blue ones remain and they pass. Okay, but over here if we place another polarizer which is called the analyzer, then obviously it will pass, and this particular plane, the yellow one, is called the plane of vibration, and it contains the plane, this contains the direction of vibration of light as well as the direction of propagation of light. So here you can see, if you consider this plane, it contains the vibration of light on it, and it also contains the direction of propagation of light on it. Okay, so that is my plane of vibration. And then what is plane of polarization? Well, that's the purple plane. Does it contain any vibration of light? No, but it contains the direction of propagation, isn't it? So what is plane of polarization? The plane containing the direction of propagation of light and which is perpendicular to the direction of vibration of light. Well, now once you have seen this figure, you have come across two new terms. And what are two new terms? One is called polarizer and the other is called analyzer. Okay, what is the meaning of that? Let us see. Well, the main difference between polarizer and analyzer is that polarizer produces plain polarized light, whereas analyzer can be used to check whether light has been polarized or not. So both of them are polarizing instruments or optical instruments. One is used for polarizing the light and the other one is used for checking it. Okay, let's now consider this figure. Well, this is my normal unpolarized light. It is falling on this crystal. This is the optic axis, and obviously you know which particular vibrations will be restricted. That is on the plane of the paper, because that is how we have drawn the axis. To check whether it has been polarized or not, we place another polarizer, or which will be called the analyzer over here, and the optic axis of both of them being parallel to one another. So what will happen? It will pass straight, okay? No components will be cut, so it is going out. So can you see light over here? Obviously. If you keep your eyes over here, you can see light coming out. Next, what we do, we rotate this analyzer by an angle of 45 degrees. Then what happens? Well, there is decrease in the intensity of light. So, since it has been rotated by 45 degrees, some of the light will pass through it, some components will pass through it, and there will be decrease in the intensity of light. But if you rotate it completely by 90 degrees, then this entire polarized light will be cut off and no light can be seen. You will have a dark view. Okay, so that is how a polarizer can act both like a polarizer as well as an analyzer. Okay. Now, there can be three types of polarized light. First one, as you have already studied just now, it is plane polarized light. The second one will be circularly polarized light, and the third one is elliptically polarized light. Now we have already seen in plane polarized light, the orientation of the light vectors remains same, but its magnitude changes during vibration. Okay, so do you remember that diagram of electric field? Okay, let's go back once again and check that diagram of electric field. Well, this one. Okay, this is a particular plane, isn't it? Now, if you check here, this particular will be allowed to pass through a polarizer. So what happens? The direction is the same of all these. But what is changing? Its magnitude, right? Okay. So, in case of plane polarized light, if I restrict only this particular direction, then what is changing? The magnitude. But the orientation is the same. So, that is what we were discussing here. In plane polarized light, the orientation of the light vectors remains same, but its magnitude changes during vibration. Now come to the second one. That's very interesting. In circularly polarized light, the magnitude of the light vectors remain same, but what changes? The orientations change continuously. Alright? And the last one, in elliptically polarized light, not only the magnitude, but also the orientation change continuously. Okay, so let us see what are the representations of this circularly and elliptically polarized light. Okay, so this one is my linear polarization, which is horizontal, restricted only along this particular x direction. Here is my linear polarization, which is the vertical direction, that means along y. And this is a combination of the two. It's a linear polarization, but it is inclined at an angle of 45 degrees. Okay, so in all these cases, what we can have different magnitudes, but the orientations must be always along the direction which is shown. But when we come to now comes your circular polarization of two types. One is left-handed and the other is right-handed. Next, we come to left-handed circular polarization, and that is nothing but the movement of your electric field vector in a counterclockwise direction with its magnitude remaining constant and its orientation continuously changing. Okay, and here is the right-handed one where its magnitude is remaining constant but its orientation is changing in the opposite direction. Okay, so one is clockwise and the other is counterclockwise. Well, in the last one, that is in elliptical polarization, we have both orientation as well as magnitude is changing. So you can see here, this is my electric field vector and it is rotating in clockwise direction, and as it rotates in clockwise direction, since my net path is elliptical, the magnitude keeps on changing too. It is maximum along the major axis and minimum along the minor axis. So when you put an analyzer, what will you see actually? Over here, you will see the maximum intensity of light when your optic axis is along the major axis of this ellipse, and you will see a minimum intensity when you place it along the minor axis of this ellipse. Okay, but the intensity is never equal to 0. And in case of circular, what will you see if you place a polarizer? You will see that always the intensity remains the same. There is no change in intensity at all. But when you take up plane polarization of light, then what do you see? If you place a analyzer, you will find that only along a particular direction you can see the light. In all other directions, especially in a direction perpendicular to this, there is no light at all. In some other cases, you can see a very small amount of intensity of light. Okay, so this is how we also can differentiate between the three. Now, a more clear picture of these three kinds of polarization can be understood from the next video. Just check it out. Okay, over here, as you can see, this is my plane polarization. Magnitude is changing, not the orientation. Orientation is only restricted along this plane, and that plane is somehow denoted by this blue line. Can you see here? Yes. And here, this is a circular polarization where my polarization is along a circle, the magnitude remaining the same, but the orientation is changing. So that is my blue circle over here. That is the projection of the circular polarization. And the last one, this is the projection of the elliptical polarization. Not only your magnitude is changing, but also the direction is changing. Okay, so let's play it to get a more clear understanding. Okay, so can you see that? Over here, the orientation is changing continuously, but not the magnitude. And here, both magnitude and orientation both are changing. Yes. And here, only my magnitude is changing, not the orientation. Okay, so these are the three cases of linear, circular and elliptical polarization. Next comes various methods of polarizing light. First one is polarization by reflection. Second one is polarization by refraction. The third one is polarization by double refraction. And the last one is polarization by scattering. Well, these two methods or these two phenomena of optics you already know. And scattering also, I hope you know that what is scattering. But what you don't know is what is double refraction. So, in our next class, we are going to study all these methods in detail. Okay, so that's all for today, students. So we meet in the next class with these 3 or 4 methods of polarizing light.